We have three hand rules to this point to describe the relationships between electricity and magnetism. The first hand rule we called the wire grasp rule. The second hand rule we called the coil rule. The third hand rule we called the hand rule for deflection. When do we use, for any of these rules, okay, whether it's the first one, the second one, or the third one, when do we distinguish between the left hand and the right hand? Jordan? Good. Use your left hand when it's a negative particle. Use your right hand when it's a positive particle. Regardless of which rule you're using, it's always going to be left hand for negative, right hand for positive. When do we use that wire grasp rule? Don't tell me how to do it yet. Okay, that's great if you know how to do it. I hope you do. But it's more important to know when to do it. Because if you don't know when to do it, it doesn't really make any difference about whether you know how to do it or not. Tell me when I do the wire grasp rule, when I use it. What am I trying to find with the wire grasp rule? What's the situation? Yep. Good. You close. You made one little mistake. Yeah, exactly. The direction of the magnetic field that surrounds a moving charge. And that could be a wire as well that carries an electric current, because really an electric current in a wire is just a bunch of moving charges. So you're trying to find the magnetic field. We'll say the magnetic field caused by moving charge. That's it. Magnetic field caused by moving charge. What about the coil rule? It's similar, but not quite exactly the same thing. When do we use that coil rule? First of all, you're going to have a coil, right? But you're not even going to use it every single time that you have a coil. You got to be careful there. Okay, whenever you have a coil and you're trying to find the direction of the polarity of that coil, then you're going to use the coil rule. So let's say you got a current in the coil, and you're trying to find the polarity of the coil. The polarity of this electromagnet that's just been produced by this electric current going through the coil. When do we use this hand rule for deflection? This is the one that we learned yesterday. This is the one that's the most different from the other two. The one that kind of is separated from the other two by an additional component here. When do we use this hand rule for deflection? Yeah, not necessarily a particle moving between two magnets, but when there's a charged particle moving through what we call an external magnetic field. Okay, the diagram that we drew yesterday and the two examples that we did yesterday, they looked something like this. You got a charged particle maybe represented by the X. You got a north pole of a magnet there and a south pole of a magnet right there. And of course, that causes a magnetic field. The charged particle is moving between two magnets. But you might also have a situation like this, where you simply have a diagram or even just a word problem that says the magnetic field is pointing downward. The charged particle, the electron or the proton or whatever it is moving towards the left. Here we've got a charged particle moving through a magnetic field as well, an external magnetic field. But we don't see any pictures of any magnets. Now ultimately, that's got to be caused by a magnet or a couple of magnets, but we don't necessarily see those magnets in the question. We do see the external magnetic field. Okay, so when do we use the hand rule for deflection? When we've got a charged particle in an external magnetic field and that causes a magnetic force. So when we've got a charged particle in an external magnetic field along with a magnetic force that's caused by that charged particle moving through the external magnetic field. How do we do it? We've got three things basically on our hand that we're going to use for all or some of these hand rules. Those three things are my thumb, my fingertips, and the palm. The thumb for the wire grasp rule is going to point which way? Which way do I stick my thumb for the wire grasp rule? The one that I'm trying to find the direction of the magnetic field that's caused by the moving charge. This is what your quiz was on today, right? Which way am I going to stick my thumb? In the direction of the charge, yeah, the direction of the moving charge. Now my fingertips I'll just write down fingers, but of course what I really mean by that is my fingertips, the ends of my fingers. I'm going to bend them. So it's going to be my bent fingers are going to point in the direction of the magnetic field that's caused by that moving charge. So if a charged particle is moving towards you guys right now, I'm going to stick my thumb, left or right thumb, towards you guys. I'm going to bend my fingers a little bit, and we're going to find that that magnetic field ends up going clockwise as a result of that. Okay, if we've got a charged particle that's moving away from you guys towards the front of the room, I'm going to stick my thumb towards the front of the room, bend my fingers a little bit. My fingers are going to be pointing clockwise in that case. What about the coil rule? The coil rule is going to be exactly the opposite. My thumb is not going to point in the direction of the moving charge or the electric current. It's going to point in the direction of the magnetic field. My fingers, which are once again going to be bent, are going to point in the direction of the current, which is the moving charge, right? A bunch of moving charges through a wire is an electric current. So it's going to look something like this. Okay, you got this thing, this piece of steel or piece of iron or whatever ferromagnetic material you have inside this coil of wire. You got an electric current, maybe caused by a battery that looks like this. Which side of that battery, by the way, is the negative side? Which side is the positive? Right or left? Negative. Which one is it, Ashton? The right side, good. The right side of the battery is the negative side, which means the current is going to go, the electrons are going to go this way. It's going to go up in the back, up in behind that piece of steel. It's going to go down in the front, up in the back, down in the front, and so on, right? So it's going to end up going counterclockwise there. We're going to use this coil rule in order to determine what the polarity of that coil is, whether it becomes north and south or south and north. Let's take our piece of paper, our little manipulative, wrap it up here, turn it into our coil. Let's make sure we're sticking our fingers down in the front of that coil because, of course, my bent fingers are going to be what represents the current here. Current's down in the front. So my fingers go down in the front. My thumb automatically points toward the left. That means the magnetic field inside the coil is to the left. My thumb always points toward the north there. So that's going to be the north pole on the left side, and it's going to be the south pole on the right side. Finally, the hand rule for deflection, the one that we did yesterday, I got a charged particle moving through an external magnetic field. It's going to be something like this. Okay, maybe a magnetic field going to the right, maybe a charged particle, an electron or a proton or whatever going downwards. Thumb goes in the direction of the particle, the moving charge. My fingers this time aren't going to be bent. My fingers this time are going to be straight. And they're going to point in the direction of the external magnetic field. So I'm going to say thumb down the page, fingers toward the right side of the page in the direction of the external magnetic field. My palm, that's the third variable that we have in our hands here that we haven't used yet. The palm is going to automatically point in the direction of the magnetic force. So thumb down the page, fingers to the right of the page, palm is going to point into the page. That makes some sense? Yep. Yep. Okay, good question. Question for the coil rule was, when do we know, how do we know whether to use our left or right hand for the coil rule? You will almost certainly use your left hand for the coil rule. The reason for that is this. Left hand is always used for negative charges. Now, when we're talking about a wire, strictly speaking, it always has to be electrons that's moving through that wire. So it's going to be your left hand. Now, there is a small possibility that you could use your right hand, and I'll explain when that would happen. Okay, it's not likely that it'll happen, but it could. Okay, about maybe a 1 or 2% chance that you might end up having to use your right hand for that. Sometimes we define a type of current called conventional current. Conventional current is the flow of positive charge. Now, positive charges can move through the air. You can have ions that are positive sodium ions moving through the air. That's conventional current. You can have alpha particles flying through the air. That's conventional current. But you can't have positive charges moving through wire. But sometimes some sources, some books will still talk about conventional current through wires. It doesn't really work that way. But it used to be assumed back in the day, before we knew any different, that that's what happened, that positive charge moved through wire. It works. Some books still use that system of conventional current because it still works. Everything we do, whether we use electron current, which is really the way it happens, or conventional current, the flow of protons, not really the way it happens, it still always gives us the same results. So sometimes sources, some books, still use this thing that we call conventional current, this flow of positive charge within a wire, but it isn't really happening that way. If that's the case, they'll tell you specifically that we're looking at conventional current. They'll probably even bold that. If you ever see the word conventional current, I want you to circle it and underline it and highlight it and put exclamation marks and circle it again and then put a triangle around it, because that's probably the single easiest thing to mess up on this year. You're so used to using your left hand, and then all of a sudden when they use that word conventional current, you just forget, and you still use your left hand. In that case, you'd have to use your right hand. But in every other case for the coil, you're going to use your left hand. It's not likely that that will happen to you, but I have seen it once or twice over the years where they say, you know, the conventional current in the wire, blah, blah, blah. They assume positive charge in that case, even though it's not really positive charges that can be moving. We still end up getting the same results. Okay? Hopefully that answers your question. All right, let's take a look at the homework that we had last night. It was page 600, question 1 and 2. I suspect question number 1 was, we might have had a little bit of trouble with both of them, actually. I think number 2 is the harder one of the two, but question number 1 is not easy either, I guess. Anybody need number 1 going over? You know, let's take a quick look at both of them, okay? Whether we need them or not. Number 1 says an electron with a charge of magnitude 1.6 times 10 to the minus 19 coulombs, and this mass is traveling west along the surface of the Earth at the equator. The magnitude of the magnetic field at this location is 10 to the minus 5 Tesla. What's the speed that the electron must maintain to remain at the same height above the Earth? So what we're saying here is this. This electron is moving through the magnetic field. It experiences a force of gravity acting downward on it. If it's pulled downward, but yet it doesn't fall downward, there must be an upward force as well to counter that. In fact, that upward force must be equal to gravity. Because if the upward force was less than gravity, it would still continue to go down. If the upward force was bigger than gravity, what would happen to it? If the upward force was bigger than the force of gravity, what would happen to that electron? It's going to go up, right? Well, it doesn't go up and it doesn't go down. So those two forces, the upward force and the downward force of gravity, must be the same value. What is the upward force? As this charged particle moves through this magnetic field, what provides the upward force? Gravity is the downward force. What is it? Cool? The magnetic force is the upward force. So for question number 1, we're going to say the magnetic force equals the gravitational force. Technically, it's the absolute values of them because one is positive, one is negative. So the magnitudes of them, right, Jordan? The magnitudes of them are going to be equal to each other. The magnitude of the magnetic force is QVB. Of the gravitational force, it's m times g. We're going to rearrange this to solve for v now. V ends up being equal to mg over q times b. And we plug in our numbers here. Let's pull with the calculator, and we'll do this as a group just to make sure that we don't mess up with the denominator here as we're dividing. Let's say 9.11 times 9.81. let's get a number on the top there. Let's divide it by the bottom. But when we divide by the bottom, let's use brackets. 1.6 times 10 to the minus 19 times 5 times 10 to the minus 5. What do we get? 1.12. V is equal to 1.12 times 10 to the minus 6. Is that the answer that was in the book? Yep. We're good there? Okay. How many people got question number 2? Okay. I'm going to actually hold off on going over it right now. We're going to spend a little bit of time today talking about that concept. So we'll wait to go over question number 2 until after we've done that. And if anybody still needs it gone over at that point, then we can go back and take a look at it, okay? What I'd like you to do right now, let's give you about 6 or 7 minutes just to take a quick peek at worksheet number 11. Give you about 5 minutes. About 5 minutes to take a look at worksheet number 11. Okay, and then we'll move on to our next thing here, okay? All right, guys, let's finish up worksheet number 11 for homework tonight. We'll take a look at it tomorrow. What I want to do right now is just take a quick look at a multiple choice question that traditionally gives people a tough time, question number 72. So let's take about 2 minutes to look at this. We'll see what you can do with it, and then we'll go over it as a class, as I say, in about 2 minutes. Okay, let's take a look at it here, everyone. 72 says moving electrons can be deflected by electric fields, gravitational fields, and magnetic fields. One electron is allowed to enter each type of field as shown below. We know that that electron has a mass, and we know that it has a charge that is negative. So we know that it's going to experience a gravitational field no matter what. If it's got a mass, it's going to experience a gravitational field whether it's moving or not. Okay. Yes, it will experience a gravitational field, and it's going to go downward as a result of that. We know that it will also be influenced by an electric field, whether it's moving or not. Now, it will experience a magnetic field, and therefore a magnetic force, if it's moving. We've got a charged particle, an electron, in all 3 cases here that's moving. So in all 3 cases, we're going to experience a magnetic field or a magnetic force, a gravitational force, and an electric force. The only question is, in these 3 diagrams, which field is which? We want the electron to be deflected downward. What kind of gravitational field do we need to cause an electron, or any mass for that matter, to go downward? If I drop this pen right now, which way is it going to go, down or up? Down. Which way does the gravitational field have to be pointing in order to cause this pen to go down? Down. So in order to cause a gravitational force on a particle of any type, as long as it has mass, to cause that gravitational force to be downward, we need to have a gravitational field that's downward. So tell me, which field is a gravitational field? Field 1, 2, or 3. If I want the force to be downward, the field has to be downward. That means field 3 is going to be my gravitational field. Now, I think the next easiest one besides gravity would be the electric field, because we don't have to do any hand rules with the electric field. So let's take a look at that one. If we want a negative particle to go downward in an electric field, which way does the electric field need to point? Good, upwards, because negative particles experience an electric force opposite to the direction of that field. If I want this electron to go downward, I need the electric field to go upward. Which one, field 1 or field 2, is the electric field? Field 1. Well, that must mean the second one is the magnetic field, but let's just double check that, okay? We've got an electron moving to the right. It says the field, whatever it is into the page. The force has got to be downward. Let's assume that that's a magnetic field. Yeah, let's make sure that it works out here. Thumb in the direction of the particle, fingers in the direction of the field, which is into the page. Magnetic force would be downward on this one. So sure enough, that field, field number 2, if it's a magnetic field, will cause the electron to be deflected downward. So what's the correct answer here? It's going to be electric, magnetic, and gravitational, A. How many people got A for that question? Okay, good. It's a tough question. Each bit of it is not necessarily all that tough. We have to know about gravitational fields, electric fields, and magnetic fields. For whatever reason, when we put it together, always seems to give people trouble, this question does. All right, let's move on here. Kind of move on, at least. Yesterday we talked about these charged particles in these magnetic fields. I want to draw a picture not only of the charged particle entering the magnetic field, but what happens to it now after it's in that magnetic field. We're going to represent the magnetic field by a bunch of X's here. That means the magnetic field in this particular diagram is pointing into the page. I'm going to introduce a charged particle now. We'll make it an electron. I'm going to switch that color, though. We're going to make it an electron going to the right. That electron will experience a magnetic force. It's moving perpendicular to the field, and it'll experience, as a result of that, a magnetic force that's perpendicular to both the field and the direction of motion of the particle. Let's use the left-hand rule for deflection to determine which way the force is acting on this particle now. Let's stick our thumb in the direction of the particle, which is to the right. Let's stick our fingers in the direction of the magnetic field, which is into the page. My palm points toward the bottom of the page. So the magnetic force is going to be downward toward the bottom of the page. That's nothing new yet, right? Now, if this electron experiences a force downward toward the bottom of the page, but it's moving to the right, where's it going to go? It's going to go, yeah, Joel, somewhere in between, right? It's going to go somewhere in between the way that it was moving and the force. So it's going to end up going down here somewhere. Down and to the right. Now let's do the hand rule on it for deflection. Thumb in the direction of the particle, which is down and to the right. Fingers in the direction of the field, which is into the page. The palm's going to point kind of down and to the left here now, right? Palm's going to point this way. So the magnetic force on it now is going to be this way. Where's it going to go now? Somewhere in between, right? It's going to end up going down this way somewhere. Let's try the hand rule again. Thumb in the direction of the particle, fingers in the direction of the field, palm points toward the left. So the magnetic force this time is going to be this way. Particle is going to end up going somewhere in between there. Thumb in the direction of the particle. You got to kind of turn your body almost upside down to do this one now. Thumb in the direction of the particle, fingers in the direction of the field, palm points up and to the left. The force is going to be this way. What do you notice about A, the shape of the path of this particle, and B, the direction of the force? Ashton, do you have one? Which one, the force or the path? Or okay, that's okay. Ryder? Path is going to move clockwise. Okay, we're not so concerned about the direction, however, that the particle goes. We're concerned about its shape and then the force. What is it? It's circular, yeah. Anytime a charged particle enters an external magnetic field, it will experience a force. We said that yesterday. But that force is going to cause it always to move in a circular path. Now, it doesn't always move in a complete circle. If it's in the magnetic field for long enough, it will go in a complete circle. If it's only in the magnetic field for a very short period of time, it'll only move in a part of a circle, an arc. Maybe a half a circle, maybe an eighth of a circle. But as long as it's in the magnetic field, it's going to move in a circular path. What do you notice about the force there, that red force, that magnetic force? It always points inward. What kind of force always points inward toward the center of a circle? A centripetal force. That's physics 20, right? Centripetal force. there is a centripetal force here. That centripetal force is given by the equation mv squared over r as it was in physics 20. But what causes the centripetal force in this? When you're driving a car around a turn, the car experiences a centripetal force, but that centripetal force is caused by friction. When the Earth goes around the sun, the Earth experiences a centripetal force, but that centripetal force is caused by gravity. What causes the centripetal force here? It's not gravity. It's not friction. It's going to be the magnetic force that causes the centripetal force here. If the magnetic force causes the centripetal force, then I can, if it's convenient for me, set the centripetal force equal to the magnetic force. So now if I see a question with a charged particle in an external magnetic field, I'm allowed to do QVB. That's what I did yesterday. I'm allowed to still do that. But now I'm also allowed, if it's convenient, to say F is equal to mv squared over r. That will give me the centripetal force, which is also the magnetic force, because it's caused by the magnetic force. If it's convenient to set them equal to each other, Fc equals Fm, mv squared over r equals QVB, then I should go ahead and do that. I'm allowed to do that because there is a centripetal force always as the charged particle is in the magnetic field, and that centripetal force is always caused by that magnetic force. So they're always going to be equal. We don't always have to set them equal. Sometimes we just don't need to do that to solve the problem. But if we do, we're allowed to. We're always allowed to do that. Make some sense? Let's take a look at this question that unfortunately isn't in your textbook. So I'm going to ask you to copy this one out, the question and the solution to it. All right, let's take a look here. This one says an electron is moving with a speed of 4 times 10 to the 5 meters per second to the right through a magnetic field that's into the page. That means that this charged particle is moving perpendicular to the field. That's important for us. Remember yesterday we said the equation that we learned, F is equal to QVB, and therefore mv squared over r, they're only valid if the charged particle is moving perpendicular to the field. If it's parallel, there is no force. If it's something other than perpendicular or parallel, then we can't do it. This question involves a charged particle moving perpendicular to the field, 90 degrees to the field, so we're good to go with it. It's moving with a speed of 4 times 10 to the 5 meters per second. The magnetic field is directed into the page, and its value is 2.5 times 10 to the minus 2 Tesla. And we're looking for the radius of the path. We're looking for how big of a circle it makes. We know we have F is equal to QVB. We're allowed to use that, but it doesn't have R in it. We know we have F is equal to mv squared over r now. It has R in it, but we don't know what F is. We know that we have Fc is equal to Fm. Let's try that. See what happens. If it doesn't work out for us, then we'll try one of the other things. Fc equals Fm. mv squared over r equals QVB. Let's rearrange this to solve for r. Notice we can actually cancel out one of the v's because we have v squared on one side, v on the other. Let's cancel out one of the v's. Now let's take the r up by multiplying. Becomes mv equals qb times r. Now let's take the qb down by dividing. It becomes mv over qb. Once we have that equation, it's pretty straightforward, right? Just plug our numbers in. If we have all these numbers. We have m, we have v, we have q, we have b. So this seems to work for us. Hold on, don't pull out your calculators for this one. There's a shortcut for this one to figure this one out. Anybody know what 1.6 times 2.5 is? 2.5 times 1.6. 2 times 1.6 is 3.2. 2.5 is 4. So it becomes 9.11 times 4 divided by 4. The 4's end up canceling. 10 to the minus 31 times 10 to the 5 is 10 to the minus 26. 10 to the minus 26 divided by 10 to the minus 23 would be 10 to the negative 3. 9.11. 10 to the minus 5. Okay, thank you. 9.11 times 10 to the minus 5, because again, the 4 ended up canceling out with the coefficients on the bottom. So that's the radius of the path, 9.11 times 10 to the minus 5. Which way is it going to bend, up or down? Well, let's just use the hand rule for that. Thumb in the direction of the particle, fingers in the direction of the field, palm points downward toward the bottom of the page. So it's going to point down toward the bottom of the page. That good? Give you a chance to copy that out for a second, and then I want to show you one application of exactly what we've just done. Then I'll assign your homework. Take a look at the picture up on the board. You don't need to copy this out. This is just another application of what we're doing, so that, you know, in the event that you see that particular application, you get lucky with it, then that's great. If you see some other application that you haven't seen before on a test or an exam, that's okay, because if we do enough of these, then surely you'll be in the right frame of mind to be able to handle that. This is what we call a cyclotron. It's a particle accelerator. Particle accelerators are used in a number of places. One of the main places we use a particle accelerator is in accelerating protons to really, really high speeds and use them for cancer treatment. Sometimes we bombard cancer tumors with protons. We try to obliterate those cancer tumors with those protons. We also use these cyclotrons in something called PET scans, positron emission scans, positron emission therapy scans. What happens is we end up trying to create these isotopes of elements that will emit positrons. As they'll do that, they'll also emit gamma rays, these gamma ray photons. What happens is we inject something into here, we accelerate them, we get them going to a really, really high speed, we collide them with some other atom over here at the target, and then we take that particle that's been produced and we essentially inject it into the body. That produces gamma rays, which can be interpreted by a computer to produce three-dimensional images of what's happening inside your body. So in a hospital, they'll have a cyclotron to produce these really quick-moving protons, sometimes for cancer therapy, but they'll also have a cyclotron in this PET machine, this positron emission therapy machine. How does it work? Well, it's actually quite simple. We get a charged particle, an ion source, right here. There is this gap that goes all the way across between these things. We call them the Ds. Okay, this gap between the Ds. In this gap, there's a potential difference. As the charged particle goes across the potential difference, it speeds up. So the charged particle speeds up here. And then it goes in a circle, and it speeds up even more here. And then it goes in a circle, and it speeds up even more here. And then it speeds up, and then it speeds up, and it keeps speeding up every time it goes around there. The way that we keep it going across this gap repeatedly is causing it to go in a circle. Now, how do we cause it to go in a circle? How do we cause this charged particle to go in a counterclockwise circle here? Have a magnetic field. Right? What do we got to do to have a magnetic field here? Have some magnets, some big, strong magnets. In the end, we need a magnetic field that points, if we're talking about a proton, that is, that we're trying to accelerate, we need a magnetic field that points into the page. if you take a look at the right-hand rule here, the right-hand rule for deflection, we would say thumb points in the direction of the particle. Right here, the particle is moving to the right. The force acting on it is a centripetal force toward the center, so it must be upwards toward the middle of the circle. Fingers must point into the page, so that means the magnetic field has to be into the page in order to cause that. Now, this isn't a perfect circle. Why isn't it a perfect circle? Why is it more of a spiral than a circle? Magnetic field is supposed to cause it to go in a circle, right? Yeah, because it keeps speeding up. The magnetic force is dependent upon the speed. So the magnetic force on it right here is a certain value causing it to go in a certain circle. But as it speeds up across the gap, the magnetic force is a different value. And then it becomes a different value. So as opposed to going in a perfect circle, it ends up going in a spiral, speeds up to the point where it goes out this little hole here as a really, really fast-moving beam, and then collides with whatever we want it to collide with. Make sense? All right. We are going to do worksheet number 12, but we'll probably have an opportunity to work on that in class tomorrow. So don't do that for homework right now. Worksheet number 11 is homework for tomorrow, okay?